Light is a phenomenon which has fascinated humanity since the dawn of time. Something in us knew it was like nothing else in the world. We could not touch it, we could not keep it from escaping, and generally could not bend it to our will. And for many centuries, we did not even think to truly ask the question of whether light followed the same rules as the other objects we were so familiar with. How could that be? Where did it come from? As we got smarter, humanity unraveled many of the great mysteries of our universe. Great thinkers couldn't help but wonder about the structure of reality itself and our most reliable way of getting knowledge out of it, sight. And how could we see without light? Light is easily the one most important carrier of information about our surroundings we have. There was no limit for this seemingly magical phenomenon. But that's where physicists, the most curious of humans, come in. Back in the beginnings of the 20th century, humanity was already aware of some of the properties of light, but did not seem to question if it could actually be affected by some object or force. By this time, Albert Einstein was developing his theory of special relativity, which, among other things, stated that nothing could ever move at the speed of light, and that since light possesses energy, then it also has momentum. The latter fact implied that light had a kind of gravity of its own, and so that it could be affected by gravity.
To talk about gravity, we need to talk about mass. If we remember, photons have no mass, but we can calculate the photons' inertial mass. The energy of an object in stationary state is equals to mc squared. And now the energy of a photon is hf. So we can calculate the inertial mass. Now, assuming that the inertial mass of a photon is equal to its gravitational mass, we wonder what will happen to the momentum or the total energy of a photon leaving or entering a massive object like a planet. Now, for entering and for leaving the massive object, we need to remember the conservation of energy. So when the photon enters the planet, its final potential energy is equal to 0. And we can see that the frequency of the photon at the ground state is greater than the frequency before it entered the massive object. So its kinetic energy is greater. When the photon is leaving the planet, if we assume that the distance is infinity, its final potential energy is equal to 0. And its initial potential energy is equals the mass of the inertial mass of the photon times the mass of the object times the gravitational constant divided by the radius of the object. And we can see that the final frequency is less than the initial frequency, so it loses energy.
So, when seeing this equation, one cannot help but wonder if ever this term, if there could be a star so massive and yet in a radius so small, with such a high density that this term could be greater than 1. Well, maybe that exists, and that would mean that for a photon to escape, it would need more energy than it has. So that is not possible, and we know such stars as black holes. where not even light can escape the gravitational pull. So how can we know what a black hole is? How can we see them? How can we detect them if not even light, not even electromagnetic radiation can escape them? How can we detect their existence? Well, there are two main ways. We can either see the light that falls into it as a spiral that gets into a dark place where no more light can escape, or we have actually detected that X-rays escape this black hole, not rather the black hole itself, but the matter that is rushing into the black hole goes at such high pressures and temperatures that X-rays are emitted to release some of this energy.
Yes. Now we are going to talk about the interactions between gravity and light. So first off, suppose we have a light beam traveling through vacuum. As you might have guessed, there is nothing very interesting in this situation, as the light beam will just follow a straight path. But then, if we added a very massive object, like a star, then there would be another situation. If we ask Newton what would happen to the light beam, then Newton would say simply that the light beam would follow a straight path, like in the other situation. He would say this because light has no mass, and so it cannot be affected by gravity, which affects only objects with mass. But this has been found to be experimentally wrong. And so, in order to explain this phenomenon, we need to ask Einstein what would have happened. In Einstein's theory of relativity, gravity can be interpreted as space curving around massive objects. So space would look something like this around the very massive star, and so the light would follow a path that would look just like that. And this is because the light is simply following a straight path in this curved space.
The reflection of light. The reflection of light is the interaction between the light and an object with a lot of mass. So when a ray of light is passing next to an object with a lot of mass, it bends inward. And it has an angle of reflection that is inversely proportional to the distance to the object. So if we have an observer that is looking to a star, he will think that the star is in a straight line through him. So, but it might be that there is an object that is between them. And because of the deflection of light, he isn't aware of this. So my friend Oscar shouldn't be able to see this star, but because of the deflection of light, he sees it 2 times. One here and one here, but it's the same star. This is because of the angle of deflection of the original star.
Summarizing, light can be affected by gravity in almost all normal forms. It can curve its path, make it gain or lose momentum and energy, and can even trap it inside and never let it go. Throughout history, light has surprised us with mesmerizing phenomena. With the classical view of the universe, we came to better understand it as an electromagnetic wave. And then, with Einstein's relativity, we learned it could interact and respond to gravity. Light has surprised us once again, and it may be that it still has mysteries waiting to be unraveled.